Okay, so we're starting into chapter 21, which is all about aldehydes and ketones. Mainly, we've already learned about their preparation, so we'll go over nomenclature and some properties briefly, and then just reactions of aldehydes and ketones. And we've already seen some examples from the previous chapter with organometallic reagents. If we look at the structure of an aldehyde or a ketone, the most important part is that carbon-oxygen double bond, or the carbonyl. We know that the oxygen and the carbon are sp2 hybridized, and that there's a significant dipole in both of them due to the electronegativity of oxygen. And so the electrons are flowing towards oxygen. Oxygen's partially negative, and the carbon's partially positive. And this dipole has everything to do with ketone and aldehyde reactivity. If we think about their reactivity and just compare formaldehyde to an aldehyde to a ketone, the reactivity actually decreases going this way. And looking at it, and perhaps envisioning, alkyl groups here instead of just an R, maybe think of a reason or two why that might be. Well, the first reason has to do with sterics. When you have small hydrogens here, this carbon is wide open to nucleophilic attack, and so can be attacked rather easily. However, since this is an sp2 carbon, there's still a good amount of room to allow for nucleophilic attack. So the second reason is probably a better one, but less obvious. We know that alkyl groups are weak electron donating groups, and they stabilize carbocations. But so if you think about, again, the dipole, that's a partially positive carbon. If it has alkyl groups bonded to it, they're able to feed in some electron density. So it's not quite as positive, or it's stabilized. Without those groups here, to stabilize that carbonyl, it's looking for something with electrons to attack, to bring some electron density. But either way, formaldehyde is quite reactive, ketones less reactive in general. In terms of properties, due to this dipole, they have moderate boiling points and moderate water solubility. So they're not capable of donating hydrogen bonds. The carbonyl oxygen is very potent at accepting a hydrogen bond. And so we know acetone is completely soluble in water. As you increase that carbon chain on a ketone, however, then the solubility drops way down. But because of this strong dipole, they have moderate boiling points. Again, not as high as an alcohol, for example. If we start thinking about nomenclature, some simple aldehydes and ketones are right here. We've got three at the top, or 3 carbons in each example at the top. And so with a 3-carbon chain, we number starting at our aldehyde carbonyl. And actually the aldehyde, as this note states, is the most highly prioritized functional group for nomenclature that we've encountered as of yet. There will be others that are higher priority, but they have priority over ketones, alcohols, and alkenes. And so a 3-carbon chain would be propane. How you make an aldehyde functional group is that you drop the E like we've done in the past for alcohols. And then since it's an aldehyde, it just becomes propanal. So you would have propanal. It's basically a shortened form of propanaldehyde, which is also an acceptable name. For a ketone, this is acetone, but that's its common name. We number to give the lowest number to the carbonyl. Doesn't matter which way we numbered in this case. But this would be 2-propan. And since it's a ketone, you drop the E and you substitute O-N-E. So it's propanone. Just like you have an acetone. You have 2-propanone, the 2 referring to exactly where that carbonyl carbon of the ketone is. You should definitely check out this appendix. It's something I've pointed out in the past, but it lists all the priorities for different functional groups, and we'll be looking at that again when we get into carboxylic acids and derivatives. Here's some other examples, however, that would be good review in terms of nomenclature. Anytime you have an aldehyde of the groups we've learned so far, you know that's going to be carbon number 1. It has to be at the end of the chain. And so we've got a 4-carbon chain. The alcohol group is on the 4th carbon. And so whenever you have an aldehyde or an alcohol as a substituent and not as the highest priority parent name, that's called a hydroxy group. And so this would be 4-hydroxy butanal. If we move on to the next one, it's a ketone. It's got some other functional groups in there. We number such to give the ketone the lowest number. And then we'll number our chain to include the most substituents as possible, including this bromo substituent. So we've got a methyl substituent and a bromo substituent coming off the chain. And so we use alphabetical order. This will be 5-bromo, 4-methyl. And so if it was just an alkyl ketone, it would be a pentanone. Since there's this alkene in there, we can insert that E into the parent name, so it'll be a pentenone. And so the alkene starts at carbon number 3. So this can be 4-methyl pent 3-ene 2-one. You could also put the 3 out here in between methyl and pent, and that would still refer to the alkene part, but this way is acceptable. Of course, if it's an alkene, we also have to think about E and Z if we're required to, and this one showcases that. And so for this alkene carbon, we've got 2 different groups to think about their priorities based on the RS system. So this with a bromine would have a higher priority. Then over here, a hydrogen versus the carbonyl group. The carbonyl carbon gets a higher priority. So these 2 groups are on the same side of that alkene. So this would be the cis or Z configuration. And so we can be complete. If you have a carbonyl as a substituent, then you have to use the term oxo. And this applies for either an aldehyde or a ketone if it's a substituent, if it's not the highest priority group in the chain. And so here again we can number our chain. We've got a hexanal, it's got a methyl substituent and an oxo substituent, and then there's another methyl substituent. And so this looks like it'll be 3,5-dimethyl 4-oxo hexanal. And now you can assign R and S to this center as well. If you assign your priorities, this would be priority number 1, priority number 2, priority number 3. So we're moving in a counterclockwise direction. The hydrogen's going back away from us, so that direction is correct. And counterclockwise is S. So that's just a little bit of review in there for nomenclature purposes. There's some good problems in the book. Page 814 shows some spectroscopic properties, specifically IR properties, and this isn't, this is more of an aside, but it explains some things we've observed looking at IR spectra for both semesters, especially in lab. And I just wanted to point it out because it answers some questions about why the carbonyl kind of moves around in the IR. If you look at these examples, they all have carbonyls, and so a carbonyl for a ketone or an aldehyde is usually right around 1700, but there's quite a big range for them if you consider all the possibilities. And so, for example, with cyclohexanone, again, the parent would be cyclohexane. It's a ketone, so we change it to cyclohexanone. A 1 is not necessary. But the IR absorbance for our carbonyl is at 1715 inverse centimeters. Okay, and that's about what we'd expect. Once you start to add in some ring strain, because that sp2 carbon wants to be 120 degrees, then that bumps up these absorbances, so they actually get higher. And so for cyclopentanone, it's 1745. For cyclobutanone, which is even more highly strained, it's 1780. And so a nice trend there. But we won't encounter highly strained rings too often. What we definitely encounter more often is when you have a conjugated system, or any pi system, conjugated to that carbonyl. And so in a normal ketone, this is a different example, we have 1709, but being conjugated actually reduces the wavelength of, or the frequency of absorption. And so with either of these examples that are conjugated, it actually drops below 1700. Effectively, due to resonance, it stabilizes where you would have a positive charge and a negative charge in a broken pi bond. So you'd have a carbon-oxygen single bond contributing to this resonance structure more when you have conjugation. And so carbon-oxygen single bonds come at lower values, so just that resonance effect kind of bumps it down a little bit. But that's just kind of an interesting aside and kind of reinforces IR spectroscopy, especially with this chapter, so important for aldehydes and ketones in general. Page 817 is an excellent page for reviewing reactions that form aldehydes and ketones. You should be able to think of 2 or 3 off the top of your head right now that produce these things. It would be worth your while to jot some down and leave a space in your notes. Jot a couple down, then look at this page and go ahead and summarize those diagrams or those individual reactions into a diagram if you want, for the preparation of aldehydes and ketones. But that's excellent and something that's review, but very helpful for multi-step synthesis problems. Okay, so the biggest part of this chapter and what we'll be spending most of our time on is reactions. So to conclude this introductory video, we'll go over the first reaction, which is similar to things we've seen in the past with organometallic reagents, and then that'll lead into the next one that's purely going to discuss reactions. We'll start off with a reaction that includes a negative carbon, something we've seen before. This will be reacting with both aldehydes and ketones. This will be extremely similar to the Grignard mechanism, so it's very complementary and a nice way to ease in to these reactions. These conditions are such where you would have sodium cyanide and then enough HCl just to maintain the pH and protonate the resulting product, which is going to be an alcohol. So it's not incredibly acidic. These conditions produce HCN, or hydrogen cyanide, which is definitely a poisonous gas. But it's the cyanide ion that actually reacts. And it's HCl that just acts as an acid at the end. And so what you get is a carbon-carbon bond formed in the reaction. This is where you have a cyano group and an alcohol group bonded to the same carbon. That's called a cyanohydrin as a product. And so ketones or aldehydes result in cyanohydrin products. You should be able to predict the product then of the following reaction. The sodium's not really involved, it's not necessary to draw, and then we'll go through and draw the mechanism. You may be able to draw the mechanism as well, and that's good. Just like with Grignards, we know that carbonyl carbon is getting attacked. What's attacking it is the cyano or the cyanide ion. And so these are relatively easy once you've worked through the Grignard reactions. Well, how does this reaction work? Cyanide is a negative carbon. That carbon has a lone pair, so it's pretty nucleophilic. Again, we'll attack here at the bottom, form an alkoxide initially. And then simply protonate with HCl. And so your byproduct is just sodium chloride, easy to purify out of the resulting organic product. In this specific case, notice we formed a chiral center. So if we draw in a little chirality here, just like before, if we're forming a chiral center, you'll get both enantiomers. And so you get a mixture. A reaction to follow this that we'll just include right below in your notes will be a ketone. It'll involve some chiral centers, but it's no big deal for us. These reactions are pretty easy. Just to get used to it, let's go ahead and throw in potassium cyanide. Why not? And HCl. And you should be able to predict the product and draw the mechanism here as well. Notice we're not reacting at this chiral center, so it's not appropriate to just say this plus enantiomer. It's always best to draw both stereoisomers. But so in this case, we have these two specific diastereomers formed. Okay, so we'll continue in the next sequence, all reactions.